Hello everyone. Today I'm going to walk you through the concept of the Arrow-Pratt coefficient of absolute risk aversion and how it measures risk preferences in economics. So I will discuss the definition, mathematical formulation and applications of risk aversion and how it helps us to understand that how individuals make decisions under uncertainty. Okay, so this concept comes from Bernoulli utility theory, which is used to measure people's preferences towards risk, particularly in financial decisions. So the Arrow-Pratt coefficient helps us understand how risk averse a person is. It's calculated by the second derivative of a utility function, and it shows how much risk aversion increases as wealth changes. The main idea here is that the higher the curvature of the utility function, the greater the person's risk aversion. This is why risk-averse people dislike uncertainty. So however, why not just use the utility function's second derivative directly? The answer is we need a formula that works across different types of utility functions, which is why the Arrow-Pratt coefficient is used. Now let's look at how different levels of risk aversion are represented. So the Arrow-Pratt measure is tied to the curvature of a person's utility function. The more curved the function, the more risk averse the person is. This graph illustrates how the degrees of risk aversion increases as the utility curve becomes steeper. So if the utility function is straight, the person is risk neutral, meaning they don't care about the risk, but as the curve becomes steeper, risk aversion increases. So this is key to understanding that how people make decisions under uncertainty. Okay, so in this slide to explore why we need the Arrow-Pratt measure, we start by comparing two utility functions. One is risk averse and the other is less risk averse. For example, if someone is presented with a small risk, the person with a higher risk aversion will demand more compensation to take on that risk. This explains why the certainty equivalent of a small risk differs for individuals with different utility functions. So this slide also highlights that the Arrow-Pratt coefficient is useful because it remains unchanged even when we apply linear transformations to the utility function. This makes it a stable measure for risk aversion. So here we see how the Arrow-Pratt coefficient is related to the rate at which an individual demands compensation for risk. We define the risk premium, how much someone is willing to pay to avoid the risk, and connect to the Arrow-Pratt measure. So this gives us an understanding of risk preference under uncertainty. So in simple terms, if we say that the Arrow-Pratt measure tells us how much more someone is willing to pay to avoid risk as wealth increases. It also shows how the utility function, which represents an individual's preferences, can be recovered using the Arrow-Pratt coefficient. So this is also shows that it is a critical insight because it allows us to quantify and understand risk aversion. So if you are making decisions under uncertainty, this measure gives a precise way to determine how much someone values the certainty. Okay, so in this section we look at how we can compare risk aversion across different individuals. The Arrow-Pratt measure allows us to determine whether one individual is more risk averse than another based on their utility functions. For instance, we might compare two individuals, one more risk averse than the other. In such cases, we can predict that the more risk averse individual would require more compensation to take on the same level of risk. Now let's compare the risk aversion across different levels of wealth. The Arrow-Pratt measure allows us to see how risk aversion changes depending on the wealth level of an individual. So we often observe that wealthier people are more willing to bear risk than poorer people, which could be due to the fact that wealthier individuals have more to lose. This concept is captured by the measure known as decreasing absolute risk aversion (DARA). As wealth increases, the demand for risk compensation also decreases. This slide introduces different types of risk aversion: constant, decreasing, and increasing absolute risk aversion. The Arrow-Pratt measure helps categorize individuals based on their risk behavior as wealth changes. So if a person's risk aversion decreases with increasing wealth, we say they exhibit decreasing absolute risk aversion. If it stays constant, they display constant absolute risk aversion. And if it increases, they show increasing absolute risk aversion. In this slide, we present an example using the CARE, which is constant absolute risk aversion utility function. So this function assumes that a person's risk aversion stays constant no matter how much wealth they have. The example here uses the natural logarithm function to show how risk aversion remains constant. So with the Arrow-Pratt coefficient decreasing as wealth increases. So this ties back to the idea that wealthier people may be more willing to take the risk. Finally, we'll look at an example of increasing absolute risk aversion, which is the IARA. Here we use a utility function with a quadratic term to show how risk aversion increases with wealth. The more wealth a person has, the more they will require to take on the same level of risk. This concept is crucial when evaluating how people react to uncertainty depending on their wealth levels. So in this slide, we are looking at the Arrow-Pratt coefficient for relative risk aversion. So the Arrow-Pratt measure tells us how much risk aversion changes as wealth changes. So it is expressed mathematically as the ratio of the second derivative of the utility function with respect to wealth divided by the first derivative. So actually what's important to note is that the Arrow-Pratt coefficient for relative risk aversion doesn't change with the wealth level at which it is evaluated. So if we say in the simpler terms, so it helps us to measure how risk averse someone is without worrying about the amount of wealth they have. So this is a constant measure of their risk preferences. This is also known as the constant relative risk aversion, which is the CRRA utility function. Here we see a graphical representation of how relative risk aversion changes with different values of B as the parameter B increases. The utility function becomes more concave here. This means that the person's risk aversion is also increasing. If we say as an example that if B is 1 by 2, 1 by 3 or 1 by 4, the utility function becomes steeper. This indicates that higher levels of risk aversion. So if we say here also in the simpler terms, the more concave the curve, the more the individual dislikes risk. This graphical representation helps us to visualize the relationship between the risk aversion and the utility. Okay, now we move on to the state-dependent utility. Until now we have been focusing only on monetary outcomes. But what if the decision maker is also considering the state of the world on nature? For example, a decision maker may care not only about how much money they can get from a lottery, but also about the state of nature, like whether there is a chance of a car accident or an economic downturn. This slide introduces the idea that the utility may change depending on the state of the world, and this is what we call the state-dependent utility. So in this case, different outcomes in a lottery can arise from different states of nature, like fear of accidents or changes in the economy. So here we see the examples of state-dependent utility. The monetary outcome of a lottery might depend on the state of nature, like whether there is a car accident or no accident. Similarly, the monetary payoff of a corporate stock might depend on whether the economy is growing or in depression. how the state of nature influences the mental pair and thus the unity derived from that pairs. So let's take this a step further by using a random variable. In this slide, we see that each state of nature has a probability associated with it, and the random variable g of s maps these states to mental pairs. For example, the random variable can assign a mental value to a correct speed or net length, and we can calculate the expected pair from these values. By understanding these relationships, we can model decision making and uncertainty more accurately. This slide continues to explore the random variable concept with complete examples. Let me see how the state of nature like a car accident or an accident influences the mental pair. The probability of each state occurring combined with the mental pair helps us determine the expected value of a particular situation. In this case of a corporate stock, the state of nature economic growth or depression also influences the pair. For instance, if the economy is growing, the payoff is high due to scope dividends, but if the economy is in depression, the payoff could be negative. Let's dive a little deeper. Every random variable can be used to represent a likely number of mental pairs. The idea here is that a random variable represents a set of possible outcomes, each associated with a particular probability. So this formula shows us how we can express the lottery outcomes in terms of mental pairs. We can select the possible pairs and the probabilities to calculate the overall expected value of a lottery. Okay, from the previous slide, we can say that we can order the outcomes from 1 to 5. This ordering allows us to calculate the cumulative probabilities, which is a key part of understanding lotteries. We see that how we can compute the cumulative probability of x of different pairs. For example, if the lottery outcomes x1, x2, and x3 are ordered from lowest to highest, we can calculate the cumulative probability for each outcome by summing the probability for all outcomes. So this is important because when calculating the overall expected value of a lottery. So also we have looked at an extended expected probability representation. We actually use this when we have a list of mental pairs that depend on different states of nature. For each state, we assign a utility value to the outcome, and the overall expected utility is the sum of the utilities for each state, weighted by the respective probabilities. So this actually allows us to model decision making where the outcomes are not only uncertain but also depending on the state of nature. Finally, in this slide, we explore the graphical representation of these preferences. First, we have the certainty line where the decision maker receives the same monetary amount regardless of the state of nature. Next, we move to the interface curve where the decision maker is fully satisfied with different combinations of outcomes. The slope of this curve helps us understand the trade-offs the decision maker is willing to make between different outcomes. Here we explore the mathematical representation of the slope of the interface curve. The slope represents the trade-off between the two outcomes on the curve, showing how the decision maker is willing to exchange one outcome for another while maintaining the same level of equity. This is similar to the MRS, which is the marginal rate of substitution that we study in the economics. By analyzing the slope, we can understand the preferences of the decision maker and how they make choices under the uncertainty. So finally, we see a graphical representation for state the utility function is state-dependent, the slope remains constant. This is an important concept because it helps us to understand how frequencies change when utility is not dependent on the state of the world. So here we begin with an example of insurance with a state-dependent utility. In this situation, the decision maker starts with the insurance, represented by the initial worth, which is a W, and the potential loss, D from an effect. So after purchasing insurance, the decision maker gets two different payouts, which is the Z1 of state 1, perhaps if an accident happens, and Z2 in state 2, perhaps if no accident happens. So if the insurance policy is actually fair, meaning it's priced correctly, then the expected payout is the zero. So represented by the equation uh, which is the zero, where the probabilities of each state that are occurring and also the budget line in this case shows the relationship between two states. So this slide explains what happens with and without the state dependency. So if we start with the without state dependency, when the utility doesn't depend on the state of nature, the indifference curve is tangent to the budget line at the certainty line. And here we can see the slope of the curve, which is negative, and the decision maker would be going to insure completely because the function level does not change regardless of an accidental occurring. Regardless of an accident occurring. So with state dependency we say, but if the utility depends on the state of nature, the indifference curves are not tangent to the budget line. The decision maker now prefers a higher payoff in state 1 if they derive more utility in that state compared to state 2. If their utility in state 1 is higher, they would prefer insurance policies that offer better outcomes in that state. So now let's a deeper look at the implication of state-dependent utility. This slide shows that if the utility in state 1 is better than in state 2, as represented by the inequality u prime of 1x, which is greater than u prime of 2x. So this implies the decision maker prefers higher payoffs in the state 1. We also see that the slope of the interface curve in this case is affected by the probability ratios, meaning that the decision maker's preferences are influenced not just by the payoffs but also by the likelihood of each state. So the graph here shows the change in the slope of the interface curve at different points. So in summary, we say that the preference of the decision maker depend on both the monetary payoffs and the probabilities of different states occurring. So if they prefer higher payoffs in state 1 compared to state 2, the interference curves and their slope will shift accordingly. The decision maker's choice is protected right now by how they weigh the outcomes of each state, and the final choice depends on the utility function in each state. So this ties back to the importance of understanding how state dependency influences risk preferences. So thank you for your attention and for watching the video. And lastly, I can say that it concludes the explanation of state-dependent utility and its impact on decision making. I hope this brought clarity how insurance and risk preferences can be modeled when the utility depends on the state of the world.